Please welcome James Kelly, VP of Market Intelligence and Innovation with the Open Compute Project Foundation, our moderator for Interconnect Insights on the Photonics enabling AI factory scale and multi-data center future.
All right, good morning, everyone. So as I was introduced, my name's James Kelly. I'm from the OCP. I always like to ask, how many of you know the Open Compute Project, OCP? Put up your hands. I can sort of see through the fog. All right, so maybe like half of you, maybe a little bit less than that. So OCP is the open source foundation and community for all things data center. We're going to be pivoting to talk about AI data centers with the panel here. But one of the reasons why we're here is we want to spread the word about the community. It is open and free. You don't need to be a member to participate in the OCP, although we've got hundreds of members. And the short history is that we were founded 15 years ago to do open source hardware server designs and have had scope creep to now basically be open source designs and specifications for all things data center, from the grid and the concrete down to the chip level. So yeah, we're going to be talking about AI data centers. And I think, obviously, the easy way to start the panel is to let these gentlemen introduce themselves, say a little bit about them, their role, and where they're from. So why don't we start with Sherwin?
Hi, and good morning. Thank you for listening to our panel. My name is Sherwin Kabatic. I'm with NTT Devices America, and my company is into optics. And so what we do is we provide a lot of the lasers and modulators, all the fancy things that transmit down the fiber. And I think this whole AI revolution is exciting for us because there's a lot more emphasis on the optics, as you guys know. So I think I'm happy to be here. And in this panel, we'll talk through some of the issues and things that we have to be wary of as we expand into this AI world with optics. So thank you very much.
Jam?
Hey, I'm John Michael Hands, CEO of Farm GPU. So Farm GPU is a neo-cloud operator based out of Northern California. So I think most of you may know what a neo-cloud is, but we're an AI cloud that is optimized for GPU-first AI workloads. We have some interesting stuff we're doing in storage and OCP networking. Yeah, I wanted to share all the learnings that we have. Yeah.
David?
Hi, David Jerpy with DataBank. We are a US-only data center operator or a co-location company with 70 facilities across the US and about 30 markets. Thank you so much.
Hi, Steve Manley. I'm a network engineer and technical lead for RDMA backend operations for Oracle. Practically speaking, that means it's my job to keep our superclusters happy, healthy, and last but certainly not least, revenue generating. And our scope ranges from the logical interface design, switching equipment, down to the L1. And part of the reason I'm here is to talk about the importance of L1 reliability and the impact that has for both the absolute scale and performance of our superclusters. Thank you.
All right, so kicking off the panel, as you can tell, we've got a different cast of characters that come from unique perspectives. And I thought it'd be good to hear from all of them, about interconnect constraints. So obviously the AI data center space is moving very, very quickly. I'm sure you keep on hearing news every single day about it. And so I thought a perfect way to kind of kick off the panel would be to hear from everyone, basically, what is a constraint today that really didn't exist a year or so ago? So what is it, and why is it a hard problem now? So I thought maybe we could start.
So 2 years ago, a big cluster would have been something in the 1 to 10 megawatt range. We're dealing with clusters that are multi-hundred megawatt and gigawatt now. And that's effectively a factor of 10 or even 100 times. The dominant limitation on scale is optical reliability. And that covers the gamut from the transceivers, but also the interconnect, the passive distribution and management. All of that performance reliability envelope sets the scale for how long a large-scale training job can run without a checkpoint or a network event, but it also sets the scale for how big we can physically make the clusters. And there is continued pressure to go bigger and faster. Managing this has become a much bigger part of what I do than I would have anticipated. When I joined Oracle, I thought I would spend most of my time tuning RDMA flows. The reality is I spend most of my time figuring out why optics are failing or why connectors are dirty. So this is a real problem, and with the help of OCP, we've started a reliability work stream specifically to look at this and new approaches and different ideas. But that's the biggest thing that's changed, this importance of the L1 layer.
Awesome. How about from your perspective, David?
Even just 2-3 years ago, a customer could come to us and say, hey, we want to deploy a megawatt of capacity, all air-cooled, and we could have that up and running for them within 3 months. Now, as you look at the AI workloads that are typically 90% water, lead times for stainless steel alone is about 10 months just for the valves and for the stainless steel. Plus, it can take upwards of 2 months to bring people in to actually put all that together. There's a lot of competition out there right now as far as just the people doing the work. And there are hyperscalers who get a lot of attention. And so that kind of leads me to what's changed over the last 2 years is that anybody who's coming to a data center operator, they really need to vet that data center operator very well and kind of understand what's going on in the industry and just making sure that they're planning ahead extremely well. They're looking at least a year out for their capacity.
How about you, JM?
So yeah, we're about 2 years old, and when we were building our first big cluster about a year ago, we talked about it at the OCP Global Summit. I would say when we were asked, like, what is the hardest part about scaling a neocloud, I would say network, without a doubt. With absolute certainty, it's network. It's consistently been our bottleneck for the last 2 years of scaling. Obviously the power and stuff is all challenging, but it's solvable. But the network, it's funny to hear Stephen talking about these issues, because we faced them exactly the same issues at a much smaller scale, and had to go do all the engineering work to go figure out how to discover failed optics, how do you train the technicians to look at the links and the quality. So that's been a big learning and a big, but I think the big change is as we're moving, from even just on the back end fabrics, 400 gig to 800 gig, going from ConnectX 7 to ConnectX 8, even in the Blackwell generation before this big jump to Vera, there's massive changes in the network architecture every single year, and so we have to basically stay on track of figuring out and pathfinding these before we go put them in production, which is often very challenging.
Let's round it out with you, Sherwin.
So from my side, I've been in the optics space for a long time, and what we normally do is we have time. So we have their first samples come out a couple of years later, then they get into modules, and then a few years after that, they get into production. I think one of the biggest challenges is we're going into our latest generation of stuff, and the month afterward, they're looking for 1 million units. And not just 1 million units, like MTBFs of, 1 million hours. And I think from my perspective, the challenge for us is hitting the performance metrics that we need, but also scaling. Scaling with quality and scaling with reliability is actually one of the biggest things. So we can come up with a bunch of optic stuff that works in the lab and maybe a couple of samples, but as Stephen had said, you need more than 1 or 2. You actually need 1 million of these things and need them to operate reliably over multiple years. And I think from a challenge perspective, I've seen that accelerate. Along with the AI curve, right? So everybody's asking for AI faster, and I think it affects the optics because we have to deliver with that kind of reliability and performance at a scale that, honestly, we haven't seen in the industry for a long, long time. As you guys all know, copper has been pretty dominant for the interconnects over the past few years, and you're seeing optics and fiber becoming much more important, getting closer to the servers and stuff. So I think from my side, it's exciting because I see lots of opportunity, but it's scary because what it's asking us to do is to have reliability to the nines and at the same time transmit at like 1.6T, which is just coming out. So I think that's really the big challenge for us, and I think that's what we're here to overcome.
All right, so thanks for sharing those unique challenges. So I wanted to anchor the audience on some terminology, right? When we're talking about AI data centers and networking, I wanted you guys to help walk through the boundaries of scale up, scale out, scale across. We hear these terms. And talk a little bit about where photonics is deployed or where copper is still winning. Maybe I'll throw it to you first, Stephen.
Yeah, so nomenclature is hard. And when you ask a bunch of different people that question, you're going to get slightly different answers. The best way, or the way I think about it, is in terms of latency. So your scale-up domain, that is your absolute lowest latency component. So that's either rack level or pod level. These are typically all rail-aligned topologies, or they're running a specific backplane within the rack, but the low latency component. To go across, that's where you start to interconnect these low latency domains, either through a different network tier or another method. But you're adding latency at that stage to build a large training cluster. Scale across is trickier. Scale across tends to be inter-building, but really when people say inter-building, you mean inter-campus. Within a building, the fiber domain is still low latency. When you start to go across campuses, though, that's when you switch from microseconds to milliseconds, and then you cross that domain barrier. So that's sort of where I think of it. The training and AI workload domain is very much in the low latency tiers, and the higher, and maybe some of the other panelists can talk to this, the scale across domain is much more about moving data than it is collective operations with AI.
Yeah. How about your perspective on that, Sherwin, since you're close to the optics?
So optics originally started on the long-haul routes, right? And so most of the data center stuff was all copper for a long time. What I've seen is that, like as Stephen said, it's kind of progressed from the long-haul routes to the scale-out, scale-across, and now infiltrating into the scale-up. I think from a technology perspective, I'm not sure how many of the audience is familiar, but there's multiple types of laser technologies, and we've gone from multi-mode, which is really dominant, to single mode now. And even now in single mode, there's multiple material sciences that we are developing to address all these different applications, right? So there's, I won't bore you with all the different acronyms, but there are different types of lasers, even within the same material science, that is developed to address all these different applications. So for example, like on the scale up, you'll see maybe an edge emitting EML, but on the scale out, you might see the same material science, but with a different type of laser technology, different type of modulator. So for us, what that means, specifically at NTT, we have to develop multiple things all at the same time. The speed of this adoption is actually unprecedented for us on the optical side. So we're used to multiple years of development for each generation, and so we're actually working on multiple generations all in parallel, all being asked to scale to a volume that we really haven't seen before. So from a challenges perspective, that's what we see. But I do think from a technology side, we're ready. I mean, on the optics side, the technology is there, but the biggest hurdle for us is really scalability and reliability. I don't think we have to develop new material sciences, but we do need to make sure we improve the reliability specifically. And then after that, scalability for cost. I mean, those are all things that we need to worry about, right? Technology is really interesting and really fun, but as Stephen said, if you can't monetize it, it's not really that useful. So I think we're really focusing on that now, and that's the challenge for us.
Okay, that sounds good. So from a NeoCloud perspective, JM, you talked about the challenges of networking. Is that mostly on the scale up, the scale out, or the scale across front?
I think it's interesting to actually look at like the unit of compute. Most of the NeoClouds are using the NVIDIA HGX. So within the box, the scale-up domain is the NVLink fabric. And if you look at the NVLink 5 versus, say, like Ethernet, they're running 1.8 terabytes a second of bandwidth between each GPU. So that's 18 lanes, and they're using 224 gig SerDes. It's very fast, much faster than anything that's running in Ethernet. So if you think about the scale-up domain within a GPU server, it's like almost 5x what the actual bandwidth is between the nodes when you're going like this scale out between node to node. And even look at one of these boxes, and right now they have 8, Connect X7s with 400 gig links, so it's 400 gigabytes a second of node-to-node bandwidth. Well, if you think about this scale-up domain, and it's very interesting to look at. I look at it from an inference standpoint. So if you're trying to optimize the TCO for inference, you want the model to fit in the scale-up domain. And it's very interesting how NVIDIA has architected the scale-up domain to match the MOE models that are being actually developed by the frontier labs. So if I just mentioned that 1.8 terabytes a second of bandwidth between the GPU nodes. Well, in the scale-up domain, in an NVLink, a GB300 and NVL72, you have 72 GPUs that have full NVLink bandwidth with the NVLink switches within the rack. That is scale-up. You're talking about 130 terabytes a second of bandwidth within that rack. And so now when you try to get in a training workload to get that to another rack, well, you're not going to get 130 terabytes a second. That's where you have to go back to the Ethernet fabrics, and then you go to all these other challenges like reliability and scalability. So it's interesting to think about. How I think about it is this domain of what is the scale-up domain architected for a single model.
Yeah, there's lots of conversation within the OCP community about copper optics at these various boundary points. So thanks for going through those. From an operator perspective, what does that do for you guys? What are the challenges that you kind of run into, David?
Yeah, one of the challenges when it comes to AI right now is that we have the universal data hall design, and we've got to build these data centers to be as flexible as possible. They're meant to last for 20 to 30 years. Just for context, they cost us anywhere between 8 to 10 million a megawatt to build. And when you're building a 500 megawatt campus, there's $5 billion in capital that we're spending. So we have to be careful with how we build these, and we want them to be able to support air-cooled environments, but then be able to pivot really quickly and support an all-liquid cooled environment. So when you take a look at the data hall and being on the floor, from a fiber perspective, it's really important to work with your data center operator on where you're going to position that cluster. You've got to make sure that the airflow across the room is sufficient. What we're doing is we're replacing our air handlers with liquid distribution units, they're CDUs, and just kind of talking, sometimes people will put all the air-cooled switches on one side of the room, and that doesn't necessarily work because there's just not enough airflow across those, and so it's just planning. It goes back to my earlier comment, when you're working with an operator, you really have to make sure that you're working very tightly with them to make sure you understand their constraints and how to properly cool your environment and not burn it out.
Yep. Okay, so let's pivot to a bit of a hot take issue. I wanted to talk about CPO versus linear or near packaged. And of course, it's a technology, at least CPO, that's been a couple years away for a long time. And Jensen and NVIDIA have kind of made it feel more imminent. Can you guys talk about the realities of if you're looking forward to deploy this, and what are the factors that you're considering as you kind of hear more and more about it these days? So I thought I'd throw that to Stephen first.
Yeah, so LPO and CPO are related, but LPO has applications independent of CPO. So when you're looking at linear optics and linear transceiver designs, the power is the consideration, but not necessarily in the way that folks think. Yes, you want to lower the power density in a rack, but that means that you're also lowering the heat requirement and management facility that goes with that as well. You lower heat, you get your reliability up. And everything goes back to reliability. How stable are these connections? Can we find ways to make them more stable? So LPO has applications in that domain, even if nothing else changes. CPO has a bunch of challenges. None of them are actually directly, from my perspective, that related to the photonics themselves. It has to do with the earlier point about you can build 1 or 10 or even 1,000 of these. How do you build 1 million and have the reliability hold? And then also, how do you design this for the realities of how data centers are constructed at scale? So you have to be able to maintain these. They have to be tolerant to certainly less than optically pristine environments. They need to be able to be serviced in these environments. There's support technologies that have nothing to do with the chip, like how does the cable management scale and is manufactured? Is that going to be reliable? The connector cages themselves and the mechanisms for high density optical connectors, how are those managed and replaced? All of these issues sort of come in, but I think it's an aside to LPO itself.
Okay. Anybody else want to weigh in on what you're seeing there?
Maybe I can comment. I think from my side, one thing that's interesting for me as just kind of an engineer is like I like problems that are based in physics. So the LPO, NPO thing, or XPO, they're addressing a physical problem, right? Copper doesn't transmit at the high speeds a long enough distance to make it useful in the data centers that we need. And so we are moving towards optics, right? So for me, that's exciting because that's kind of a line that needs to be drawn. And so the optics piece to it, obviously from my company and the fiber world is excited to have happen. But I think one thing that we are trying to do is we are trying to fit inside data centers, standard data centers with racks inside of a plant that has a fixed power supply that we're trying to fit all these faster and faster GPUs into. And so one of the technologies people are coming up with is CPO. And so what CPO does, for example, just as one example, it tries to take away some of those copper limitations by reducing the copper links, right? So you're trying to reduce that copper loss from your GPU to the outside of the box to, instead of inches, to centimeters, right? So that's a good solution for reducing the loss in copper. But what it does do is it pushes the optics, which we are interested in, to fill up the rest. And I think, again, maybe we're beating down the same point, but what we're supposed to do is really address all these new, faster applications, but meet or exceed the paradigm of reliability, power consumption, replaceability. Actually, that's one thing we didn't talk about from a CPO perspective. Replaceability becomes different. You can no longer unplug something that doesn't work, plug in something new, and you're up and running. Actually, the solution might be to undo the whole rack and put in a new rack. And that piece to it is something very new. And I think from a reliability and cost perspective, that is a problem that the industry is trying to grip with right now. I mean, I think there isn't a clean solution for that.
Yeah, I think there's also some other enabling technologies that are going on. I'm very excited about EBO in the connector domain. That has the promise of significantly improving the biggest failure point on optical connections, which is the interfaces themselves. And the promise of EBO may be that it also enables new technologies like CPO approaches to be practical in the environments that we're working in right now.
Okay, so I wanted to pivot to not just talk exclusively about photonics, but some of the higher level topology-oriented questions, which are important and evolving quickly within AI data centers. Obviously, there's, we know of like front-end, back-end, storage fabrics, and even within back-end, there's things that are changing. So as we see, new designs, port counts doubling on switches, higher radix growing, how does that change how you guys are designing and buying? Maybe I'll throw it to you, JM, from a NeoCloud perspective.
At the OCP EMEA Summit in Barcelona, we just announced with our partners at Celestica and Hedgehog, we have an open network fabric reference architecture in OCP now. So you can go to the contributions page, and there's two reference architectures. One is for training, and one is for inference. And in those, so one, it's nice that we basically open sourced with our partners the entire blueprint of actually how we're designing the topologies in the data center. And they've designed it to be able to be flexible with different XPUs. In this case, we used the Broadcom Tomahawk 5 architecture, but they have in that OCP topology, it basically shows you how many switches you need for different XPU domains, from like a small cluster of like 8 nodes all the way up to like 256 nodes with 8 XPUs or GPUs each. And in the two architectures, what we're deploying is the Quas. For like our very first cluster we built was like a really tiny 32 node cluster. So it was literally 2 spines, 4 leaves on the back end fabric. And going back to the co-packaged optics thing too, I'm just trying to think through like this flexibility. It's really nice. When we think about these topologies, it's all about TCO. if you look at the average network cost of a GPU cluster, if you have a full back-end fabric and the front-end fabric, it could be between 20 and 25% of the TCO of the entire cluster. So it's a non-trivial amount. So it wouldn't make sense to go build all that network fabric if you're not going to use it, or if it's been poorly designed. So anything that we can to basically move the needle, say 5 or 6%, by going from the CLOS to a rail topology, and we're talking about the different layers to add redundancy. You have to look through not only just like the complexity of the network design, but the TCO is actually the most important metric, because we have to pass that through directly all the way to the customer. So if it ends up being, basically the way neoclouds think about this is you take the total network cost of a cluster and divide it by the total number of GPUs in the cluster, and you have now a $1 per hour per GPU that is the back-end fabric of the network. And that could be between 60 cents and $1 per hour per GPU on a large training cluster. So it's not insignificant. If we have to pass that through to our customer, it has to be like properly designed, and which is why we went down this whole OCP path in the first place. We were the first neocloud to say, well, we're not just going to blindly do the NVIDIA reference architecture. Let's go figure out what the actual cost of this should be from first principles, and then build it, architect it the right way. I think you think these AI customers that are renting training clusters are sophisticated. A lot of them are just like, hey, we're told we need InfiniBand. We're like, okay, do you need InfiniBand, or do you just want them all? Do you want a back-end fabric so they're all connected to each other? They're like, yeah, that one. So, it's interesting. But yeah, as I mentioned, TCO is like absolutely the most critical, because we can't design a network without thinking about the cost.
So Oracle's got a lot of different topologies that are massive. Some of the things that we talked about in ideas surfacing for this question was like the multiplanar fabric.
Yep.
Stephen, can you talk about that? Or, I mean, another thing that this audience might know of is OCS and the optical circuit switches floated role. I don't know that there's a lot of OCS deployed in data centers yet, but increasingly it's becoming an interesting
Absolutely.
tool.
So everything is about trade-offs, right? And it's important to remember that over a cluster's lifetime, it may be utilized for different purposes. So what started out as a large training cluster, as the technology ages, may turn into an inference platform. And everything is about trade-offs between flexibility and, design for purpose and core performance. When we look at this, we also have to weigh use cases for multi-tenancy. So our fabrics are bare metal, but they're also multi-tenant. And as networks get flatter, traffic is exposed to other traffic, and effectively you need to manage this congestion. So those are the weigh-offs. I mean, multiplanar has great advantages in that the overhead cost, the TCO calculation, ends up being a little bit lower, but the network is flatter, so that may cause complications for multi-tenant configurations, whereas if you have a specific single customer running a synchronous, coherent workload, it may be the absolute ideal situation in fabric. So these all factor in. The OCS discussion is related. Switching gives you infinite flexibility. So you can change things, you can apply rules and priorities and queues, but it comes with a price, and the price is the pipeline and the processing to look at the packets and figure out where they need to go. OCS gives you a flat circuit approach where there is very little latency, but the trade-off is that you can't switch quickly. So I think as workloads become more adapted to longer-lived flows and more stable configurations of flows, technologies like OCS will become more widely adopted and looked at. Right now, I don't think there's a lot of it in the space, but it's exciting to look at, and it's obviously something that we're looking at as well.
Yeah. Okay, so maybe to talk about campuses and data centers, to throw one to you and DataBank, David, right? We talked a little bit about scale across, and there's some mention of like training, scaling across multi-data centers here, and certainly NVIDIA's talked a lot about that, so we hear a lot about it. You guys operate multiple campuses, multiple data centers. When it comes to like planning for that, the realities, the photonics that interconnect them, can you talk about what's enabling that and what the challenges are, what's in the way?
Yeah, absolutely. What we're seeing, we're working with a cloud service provider. They are, instead of going with the traditional telcos and bringing in a lot of different 100 gig links, they're preferring to go with dark fiber and going with dark fiber companies that have set up rings in I live in Atlanta, so they've set up a ring between the major carrier hotel, which is 56 Marietta, and then all the other different data center providers in the area, and are connecting all these together with very robust backbones. This same company came to us and said, hey, you need to make sure that you have 4 egress points from your data center, north, south, east, west, so that they can peel out of the data center and not have any of the dark fiber from the different providers cross over each other. So that's kind of been something that's become more and more important, is dark fiber in a metro.
So I'll leave it kind of open. Looking at the clock, we'll move to the last question, but anybody else want to kind of weigh in on the scale across multi-campus
Just one
challenges?
one
Yeah.
topic on the optical side. I think you guys talking about fiber utilization and switching fibers. How it affects us at the optical level is that we're moving to technologies that optimize the fiber. So, for example, bi-die, right? So bi-die, you can get bi-directional signal down the same fiber. So 1 fiber instead of 2. DWDM, a very classic strategy that's been around for many, many years. We're implementing across different wavelength ranges, actually, right? So you can do it around the 850 range, you can do it around 1310, you can do it around 1550. So again, from our perspective, all the topics that David and Stephen had talked about affect the physical layer, because we do have to make sure that we have the optics to match that. So not just the fiber, but then the transmit and modulator technologies to implement OCS, right? It's different than we've had in the past, and so that's one thing that's new and different that we're also adapting to these new challenges.
Okay, terrific. So we started off the panel kind of talking about what is a challenge right now and why that wasn't, kind of looking backwards and comparing. Let's sort of flip that and say, looking forward a year, or Fiber Connect in Nashville next year, or OCP Global Summit ahead of us, what do you anticipate are going to be challenges that we haven't talked about, or you feel like are not probably talked about enough? Maybe we'll just kind of go down the line, starting from Stephen.
Yeah, so look, the last couple months, AI works. The implications of that are pretty big. We build AI factories. So what do the factories produce? They produce AIs. A car factory produces cars. What do cars run on? Gasoline. AIs run on tokens. And I think the next year is going to bring a significant emphasis on all sorts of technologies to design networks around inference. I don't know necessarily what that looks like, but we have to power the machines that we've built, and that's going to be done with inference. So I think that's going to become a much bigger discussion over the next year, and that may change how some of these fabrics are built and designed or transitioned, but that's what I think we're going to see a lot more of in the next 12 months.
Table stakes in our industry is going to be any new facilities that are built are liquid enabled to be able to support these AI workloads. What's going to be something that we need to figure out is we have a lot of legacy data centers that are predominantly air-cooled, and they don't have water loops in them. So just figuring out how to use sidecar solutions as an example to be able to bring water to these facilities in a closed environment and be able to support these more dense workloads is the challenge that we're faced and we got to figure out.
Yeah, I should have prefaced this with I'm actually not a network guy. I'm a storage guy. So and it's been building up that capability within my team. So I think one of the big bets we're making is that storage is going to be one of the new barriers, especially for inference as we scale with KV cache context and actually inferencing bigger models. And we're basically planning ahead, and being this experts in both storage and networking will have this kind of unique advantage. But we're architecting these solutions that like on the storage bandwidth, we're talking about hundreds of gigabytes a second per node, so stuff that hasn't been done. So it just, our customers keep pushing the boundary of like what they want, and we're pathfinding like what we think that they're going to, where the puck is going, which is going to be planning for massive growth. As Stephen said, as we're a small company that has massive leverage due to AI, and I can't think of another way of doing it. And it's just getting. We were just talking last night over some beers about how crazy it's going to get in 6 months, and like it's almost impossible to think about because we're just trying to keep up with the new model that came out last week, and like trying to make sure that's in our workflow and getting ready. So if you plan ahead, for what's going to be going on next year, just plan. I mean, the guys that are running the frontier labs keep saying it. Plan for the models to continue to get better. They will absolutely get better, and you absolutely have to. We're going to be taking massive and full advantage of that.
So from my side, I think a few years from now, what we'll do is we're optically, like for years, what we've done is we've tried to go faster and faster, right? That's kind of what we've been doing for 30, 40 years. I think in 5 years, it's actually going to be different. What we're going to try to do is design for power consumption and reliability. In fact, what I've seen is that, at the newest generation, newest speeds, we're resurrecting old technologies which were thought to be obsolete, because they were actually much more efficient power-wise than the newer stuff. So again, the need for speed is always going to be there. However, I think designing around the power consumption and making sure we're power efficient as much as possible to get to these speeds. It isn't breakneck speed at the expense of power. I think we need to balance that, and making sure that our technology profile is able to deliver 1.6T, for example, at power that is equivalent to 800 gig. I mean, those are kind of the challenges we have today. And I think that's going to be different. That's different from where it was 10 years ago, and 5 years from now, I expect the paradigm will shift in that direction.
All right. Well, that's a wrap for our panel. I want to thank everyone for your time and trust, and the Fiber Broadband Association for having us. Let's put our hands together for the panelists.